Hey everyone, welcome back to Math 111. This is Scott. Let's get started. What we're going to talk about today is a couple of sections, 6.4 and 6.5. And from 6.4, we're only going to cover a small fraction of what there is on offer in your book on that section, because that's all that really applies to us in this course. So 6.4 has to do with what has to do with the graphs of logarithmic functions. Here's the basic idea. Well, what is a logarithm anyway? It's the inverse of an exponential. Are inverses to exponential functions. And what's the deal with inverses? They switch x and y. So thus, their graphs are the result of switching the roles of x and y from the corresponding exponential graph. Alright, well, last section we nailed down exactly what the properties of exponential functions were and their graphs. So what we can do now is try to take that information and turn it around to make information about logarithms. So we can take exponential facts and turn each of them around to make a logarithmic fact. Alright, well, first off, when it comes to exponential functions, we can say, generally speaking, what the graph would look like. So, or first let's start with what the formula would be like. So the formula here would be y equals b to the x. So we're not talking about any kind of transformations here, just a naked basic exponential function. And the corresponding formula on a logarithmic world is going to be y equals log base b of x. So these are the two sides of the corresponding coin. Okay, now for exponentials, we know that the domain is all real numbers. And what that would then tell us is that the range of every logarithm is also all real numbers. So negative infinity to infinity. The domain of a function is the range of its inverse. Conversely, the range of an exponential function is 0 to infinity, which means the domain of the corresponding logarithm also is 0 to infinity. So range becomes domain, domain becomes range. Now the graphs can come in two flavors. One is if b is greater than 1. It's what most people think of when they think of exponential functions, and that is exponential growth. Or b less than 1, which is the same story but in reverse. It's exponential decay. But now let's think about what the graph would look like in the inverse. So the inverse situation would turn every horizontal fact into a corresponding vertical fact and vice versa. And so, for one thing, the y-intercepts will become x-intercepts. So say b greater than 1. So this was 1 and 1, and this is always going to be 1 as well. Now, every exponential function has a horizontal asymptote, which means that the logarithm has a vertical asymptote. So there's a horizontal asymptote at y equals 0, which makes a vertical asymptote at x equals 0. And notice that here it's getting pulled up in the direction of the y-axis, which means this one's going to be getting pulled out in the direction of the x-axis. And then b less than 1 is going to be the reverse situation. So, but now the reverse, basically you can think of this one as being a horizontal reflection of this one, which means that this one is going to be a vertical reflection of this one. And then one more fact that is of note about exponential functions is that they always have a horizontal asymptote at y equals 0. So these always have a horizontal asymptote at y equals 0. Conversely, the logarithmic functions have a vertical asymptote. And that's at x equals 0. Now, one last thing to discuss here is the effect that the b has on the shape of the graph. Well, in exponential graphs, having a higher value of b means a steeper growth, meaning a steeper increase in y. But the inverse situation would be a steeper growth would mean faster increase in x, in other words, shallower growth. So for b greater than 1, higher b leads to slower growth. So for example, if we had an exponential function like this, that would mean a relatively shallow, a logarithmic function like this would mean a relatively shallow growth. So this would be like log maybe 3/2 x versus one that was growing a little bit faster, growing a little bit slower, which would mean something more like this, which could be, say, something like ln x. And remember, ln is b is e, which is approximately 2.7. And then maybe we have an even shallower one at, say, log x. Remember, in the case of log, b is 10. And any in-between b's would be somewhere in between those. And if b, on the other hand, is less than 1, then we can run the whole story backwards. So then basically the closer b is to 1, the shallower. Sorry, the less shallow. So we should say if b is less than 1, lower b implies, so lower b implies slower negative growth. So this could be something like, so this one is relatively faster, so this could be something like the log base 3/4 x versus something that was, oops, growing a little bit shallower. So this could be something like log base 1/2 x, etc. Now, when it comes to actually sketching the graphs of logarithmic functions, one thing that's helpful is to fix on a certain key point to help anchor your graph. Sketching graphs. So some key points to know. So y equals, I should just say log base b, could be any log, could be a natural log, could be a common log, could be a log base anything else, of x. So some points of interest. There will always be an x-intercept at 1, 0. There will always be not a y-intercept, but a vertical asymptote at x equals 0. Let's see, and then there will always be like what's called a key point. Which is going to be at b, 1. So as an example, y equals log x. Well, there's always at 1, 0 going to be an x-intercept. And then the key point is at 10, 1. So then what that means is we got to go up through there and then level out to go that way. Now, shifts and other kinds of transformations can all affect all of these key things. So, function transformations change all these landmarks. And in particular, let's discuss what we would do if we wanted to do something like find the domain and the vertical asymptote of a transformed function. So finding domain asymptote for transformed logarithms. So the idea is take the input to the log, set up the inequality, whatever it is greater than 0. Solve for x. This gives the domain. Then the x value that corresponds to the log input being 0 is the new vertical asymptote. For example, let's say what we had was something like this. Let's say, so find the domain and vertical asymptote of y equals log base 3, and the base here is totally irrelevant actually to what we are going to be doing. It's all going to be the same no matter what the base of the logarithm is in this regard. And then I'll say it's 2x minus 2. Okay, well, first off the domain. We take the 2x minus 2, the input of the logarithm, and we set that greater than 0, and we solve for the x. So then that's going to be add 2, divide by 2, and get x greater than 1. So the domain is going to be x greater than 1, which is in other words 1 to infinity. And then that specific value, that value is the vertical asymptote. So then what that means is the vertical asymptote is going to be happening at x equals 1. So it's going to be the border value of this. Alright, well that's, like I said, all we're going to really be talking about in this particular section. It's a short topic for us. It's a longer section in the book, but the book covers stuff that is beyond the scope of this course. And then the other section for this lesson is section 6.5, where we're going to discuss some of the properties of logarithms. So this is actually a thing that that used to be an even more important matter than it is today. For centuries, the main use of logarithms in the actual practical world was because of these properties. They were used to to calculate things like multiplication, division, square roots, other kinds of roots, powers, things like that. So this is what logarithms were actually originally designed for, and that's how things like the slide rule work. But for us, we're just going to look at a few properties, and we're going to discuss it mostly from an algebraic side. So the idea here is that there are properties of logarithms that correspond to the properties of exponents. We can use these properties to either, one, condense a complicated expression into a more compact one, or two, we can go the opposite direction, which is expand an expression into more terms, each of which is simpler, or three, evaluate an expression. So depending on what exactly we're dealing with, we can either write it in a more condensed way, a more expanded way, or we can actually just get a straight up value out of it. Now, here are the properties of logarithms that we're going to be making use of. Properties we'll use. Alright, so first off, let's think about the properties of exponents that we know and love. So first, a review. Of properties of exponents that are relevant. So first off, let's say we had b to the a times b to the c, something like that. Well, if the base is the same, then this means a copies set beside c copies. So that's going to be b to the a plus c. Let's say we had, on the other hand, b to the a divided by b to the c. Well, once again, this is like a copies of b, this is like c copies of b. And c of the copies are going to end up canceling out from the a that were there. It's going to be a minus c. And then if we had something like b to the a all raised to the c, then that will be the same as a copies of b, a copies of b, a copies of b, repeated c times. So it's like there would be a total of a times c copies of b all in a row. Let's see, and if we have b to the a, let's say the c root of that, so this is kind of the reverse of this, then this would be b to the a divided by c. Let's see, other important facts. What if we have 1 over b to an exponent? Well, that's going to then give us negative, b to the negative a. Also, b to the 0 equals 1. It's a fact. And b to the 1 equals just b. So these are some of the properties, So these are some of the properties of exponents that we will be recycling into a logarithmic setting. Now, the logarithmic versions of these same properties. Well, the first one that we said was the one where if you multiply two things with the same base, that's the same as adding their exponents. But logarithms are more like asking you, what were the exponents? So this, if we read it in reverse, would be log base b of, and then here, if we had x times y, and this is the same as log base b of x plus log base b of y. So this is like saying, how many times can I squeeze a b into this product? Well, it's however many I can squeeze into the x, plus however many I can squeeze into the y. So, in other words, log base b of something times something else is equal to log base b of the first thing plus log base b of the second thing. Okay. Similarly, the log base b of x divided by y, well, that's the same as the log base b of x minus the log base b of y. And then, so that corresponds with the subtraction side of things. Now, if we are talking about a power raised to a power, then the logarithmic equivalent of that is, if I took log base b of x to the power of y, then that's the same as saying x times x times x times x times x, y times in a row. And if it's y times in a row, then that means the overall number of x's I'll be able to fit into this product is however many, the number of b's I'll be able to fit into that product is however many b's I can fit into a single x, and that will be multiplied by a factor of y. So in a sense, it's like the exponent just came down to the front. And then other things that correspond to the other properties. So log base b of 1 will equal 0. Log base b of b will equal 1. And then as far as all other operations, we can treat any roots as fractional powers, and things that are in the denominator can just be thought of as having negative powers. items in the denominator. We treat it as negative powers. Now, before we do any examples here, I want to warn you. Warning. I want to warn you about something. We have rules for log of this times that, this divided by that, this to the power of that. We don't have any rules that pertain to log of sum. So there are no ways to simplify logs of sums or differences just products, quotients, and powers. So for example, log base b of x plus y, this cannot be simplified. Okay, so now let's actually try using this. So to actually use this, we can go in a couple of different directions. One is to condense, one is to expand. So one note about this, all of these properties require the base to be the same, and all of these properties work in two directions. All of these properties work for any base b greater than 0, and for, and this, or I should say this including ln and log, the log base e and the log base 10, the natural log and the common log. So all these properties work for any base, and all of these properties work both directions. So by that, what I mean is you can go from one direction to the other, or the other direction to the one. So let's see. So let's just try, for example, to use these. So for example, condense. The following to a single logarithm. And for example, what we might have is something like log log of 5 plus log log of x minus log log of y. So in this case, what we have are the log base 10, and what we have is a sum of two logs and a difference also. So this we could actually just write as, first off, log 5 times x minus log y. So I've just combined these, so this was log this plus log that is the same thing as log this times that. Logarithms are the bridge between addition and multiplication. And then here, now we have a difference of two logs of the same base. So that's going to be log this divided by that. So there it is now expressed as a single bare logarithm. Now another thing we could have would be something like, let's say we had the log base 3 of 5 plus the log base 3 of c plus the log base 3 of 10 plus the log base 3 of d. So here we can basically just again use the fact that the sum of logs is the log of the product. So it's going to be log base 3 of 5 times c plus log base 3 of 10 times d. So I'm just basically doing those. And then here, once again, I can put those all together. So this is equal to log base 3 of 5c times 10d, which is actually just going to equal the log base 3 of 50cd. And the takeaway here is that we can actually just put all the factors together. We don't have to go pair by pair. We can just multiply them all together. So put all factors together. Okay, so there's that. Now, another thing we could do would be something like this. Let's say we had the log base A of 35 minus the log base A of 5. Well, here we have a subtraction of two logarithms. That's the same as the logarithm of the divisions. That's the log base A of 35 over 5. But in fact, actually, those have a common factor, so this can be simplified down to the log base A of just 7. Now, what if what we had was something like d? The negative natural log of 1/10. So natural log, remember, is the log base e. Well, the negative here is a factor that can be brought into the expression, and that's going to make 1/10 to the negative 1. But when you raise something to the negative 1, that's the same as just flipping it. So it's the natural log of just 10 over 1, or just 10. And then other things we could do, we could have something like 1/2 times the ln of 25. Well, once again, a factor up front can be brought up as an exponent, and so that's going to be ln 25 to the 1/2. But a 1/2 power is the same as a square root, and a square root of 25 is in fact just 5. Okay, so this is how the condensation works. You just take the various pieces and you use the properties to squeeze them all together. It's important in this that they all had the same base. If they didn't have the same base, it wouldn't work, but that's not going to be very often that we're going to see logs of different bases. Now, the other side of this is expanding. Expanding into multiple terms. Now when it comes to this, we have to actually be very cautious about the order that we do this in. We have to be very careful about first organizing it as a logarithm of a division, or of a product, or of a power, or of a root. So basically here, so we go step by step from the middle operation outwards. So for example, let's say what we had was something like the log, let's say the natural log of x to the 7th times y to the 3rd divided by z to the 5th. Well, first and foremost, this is equal to the ln of something divided by something. That's what is fundamentally going on here. It's something divided by something. So what that means is we are going to first and foremost break it up there. So natural log x to the 7th, y to the 3rd, minus the natural log of z to the 5th. Now right here, what we have is a log of a product. So it can be broken up into log x to the 7th plus natural log y to the 3rd minus natural log z to the 5th. But now, at this, so here what we had was ln something times something. Now here what we have is ln of something to the power of something. So the power comes down. Boop. Boop. And boop. And that means we've got 7 natural log x plus 3 natural log y minus 5 natural log z. So once again, we had to work our way basically from the inside of each logarithm outward. You want to say, is this a logarithm first and foremost of a product, of a quotient, of a power, of a root? Now, it wouldn't be any different if we had something like the log log of. And maybe we had a to the negative 2 divided by b to the negative 3, c to the negative 4. we would start by asking ourselves, first and foremost, is this a log of a product, a quotient, or a power? And it is the log of a quotient. So that means we're going to have log a to the negative 2 minus log b to the negative 3 c to the negative 4, which is going to be log a to the negative 2 minus, now here, this is a log of an addition, sorry, of a log of a product, which is going to make an addition. But because of this negative, it's going to distribute to both of these. So we're going to have log a to the negative 2 minus log b to the negative 3 minus log c to the negative 4. So that was nothing logarithmic we did there, just algebraic. And then, finally now, we have a log of a power, a log of a power, and a log of a power. So the exponents all come down. So it's going to be negative 2 log A minus negative 3 log B minus negative 4 log C, which is then going to just be negative 2 log A plus 3 log B plus 4 log C. Okay, now, what if what we have was something like this? So let's say we had the natural log of the square root of x to the 5th and y to the 3rd. Now, first and foremost, this is something that needs to be rewritten in a different format, because the square root in all logarithmic operations is going to be best thought of as an exponent. Logarithms are the inverses of exponents, so everything should be put in terms of exponents before proceeding any further. So this is ln something to the something. So what that means is the something comes out and now all of a sudden we've got a logarithm of a product on the inside there. It's going to be 1/2 times ln x to the 5th plus ln y to the 3rd. But that 1/2 distributes. So we're going to have 1/2 ln x to the 5th plus 1/2 ln y to the 3rd. But now, once again, here we are in a situation of having natural logs of exponents. So the exponents come down and they multiply. So it's going to be 5/2 ln x plus 3/2 ln y. Now, you may do these in a different way, and if you do, you should get something that ends up being equivalent. It may not look the same at first, but it should, in the end, be equivalent to whatever you do by some other way. So C, so now for D, let's try something like this. Let's try the log log of x times the cube root of the division x minus 1 divided by x plus 1. This is a cube root. Alright, well, first off, this is a log of something times something. That we can tell because the middle operation of this, the central operation here, is something times something. It's going to be log x plus. Now at this point, I'm going to also rewrite the cube root as a 1/3 power. Cube roots are 1/3 powers, and it's almost always an advantage to write it in its exponential form for these. But now what we have here is a log of something to a power. So we have log x plus 1/3 log x minus 1 over x plus 1. Now here what we have is a logarithm of a division, and logarithms of divisions can be rewritten as a subtraction of two logarithms. And then finally that 1/3 can be multiplied in so log x plus 1/3 log x minus 1 minus 1/3 log x plus 1. Now, a note on this, you don't really need parentheses as long as it's a log of a simple solitary thing, but as soon as it's a log of more than one thing, then parentheses become necessary. So if it's more than just one simple thing, then you do need to put parentheses in order to indicate the beginning and end of the logarithm. Now let's take the natural log of x to the third y squared square root of x to the fifth y squared. Now, first and foremost, we can think of this as being just a logarithm of a product. So this will be the first one, and this will be the second one. And while we're at it, we will discretely, at a point of our choosing, rewrite the square root as a 1/2 power. Now at that point, that becomes the central operation here. It's whatever that is, all to the power of 1/2. Here, we've got a product. So it becomes a sum. Here we've got 1/2. ln x to the fifth y squared. And so here, like as we go, we were waiting before until we had everything at kind of the same level before we did any simplification, but that's not necessary. We can do a lot of things kind of in parallel here. And we got it as 1/2 ln x to the fifth plus ln y squared. And that is all under the influence of that 1/2, and so it'll be necessary to distribute it. So 1/2 ln x to the 5th plus 1/2 ln y squared. And then here we're going to have 3 ln x plus 2 ln y plus 5/2 ln x plus, multiply the 2 and we're just going to end up with ln y. Now we can combine like terms. So those are all the things that are the ln of the same thing. So what that means is we're going to have 3 plus 5/2, so 5/2 is the same, so 3 is the same as 6/2. So that's going to be a total of 11/2 ln x. Combined, so that's going to be 11/2 ln x. And then combining the other two, that's going to be 3 ln y. So we can combine like terms in an expression like this. Alright, now we can also take expressions of a form similar to this and condense them into a single algebraic expression. So let's do an example of that. Condense into a single logarithm. And we could have, for that, something like this. We could have ln 2x cubed plus ln 5x squared. Now here, because we have a sum of two logarithms, we would just multiply together what's inside each. So those get multiplied. But then once it's in this form, we can actually execute the multiplication. So 2 times the 5 is going to be 10. And x cubed times x squared is going to be a total of x to the 5th. Similarly, we could do it with a subtraction. Let's say we had log log. Let's just take the more or less the same things. One little change, I'll make it 20 x cubed minus log log 5x squared. And here then, if we wanted to deal with this, we could just rewrite them as a division. But these have some common factors, and this cancels a little bit. And so we have log log of 4x. And as one last thing that we could have is factors in front. And this can come in a couple different ways, so let's just see them both. So we could have 3 times ln x plus 2 times ln x minus 1, and then let's say minus ln x plus 1 divided by 2. And let's see what that leads us to. So first off, we can bring exponents in rather than taking them out. So this is going to be ln x to the third plus ln x minus 1 squared, and then minus, I'll rewrite this one as just first step, I'll just rewrite it as ln, as 1/2 ln x, x minus 1. And then we can put them together and get ln x cubed times x minus 1 squared, and then minus ln x minus 1 to the 1/2 power. But a 1/2 power is the same as a square root. Sorry, plus 1, x plus 1, x plus 1. So a 1/2 power is the same as a square root, and the subtraction is the same as a division once you've done the logarithms. So we're talking here about the ln of x cubed times x minus 1 squared divided by the square root of x plus 1. So there's that. And then there's one more important property that we're going to have to use in order to make the most out of these logarithms, and that is the change of base formula. So change of base formula is a way that we can evaluate all of the irregular logarithms. So we can evaluate log base 10, log base e on a calculator, but none other. So change of base formula is our patch for that. Change of base formula. If we are given a logarithm of base a, we can change into any other base, let's say b, via the following formula. So if I had the log base a of x to start with, then I can rewrite that as the log base b of x divided by log base b of a. So this is often called log big over log little. As a mnemonic device. Now, as an example, we might want to change something like the following. A, let's say what we had was the log base 3 of 29. We wanted to change that to base E. Well, here we have currently log base 3 of 29. So base E is going to be ln 29 over ln 3. And the reason why this works is basically, if you think about this, this is saying, how many times does 3 go into 29? Well, who knows? Like, how many factors of 3 can go into 29? Who knows? But this, we can use a calculator to figure out how many factors of E go into 29. And then this is how many factors of E go into 3. So if you want to know how many 3's go into 29, it's how many E's go into 29 divided by how many E's go into 3. And then we can actually evaluate this in a calculator without any trouble. But let's just try one more here. Log base 5 of 27.31. Let's say we want to change that to base 10. Well, log base 5, 27.31, we already know that it's going to be 27.31, and then 5 on the bottom, and it's just a question of which new base we want, and if we want a base of 10, that'll just be the common log. Log this over log that. And then this is how you can evaluate unusual logarithms on a calculator. So you can use this to evaluate logarithms on a calculator. Or graph logarithms on, for example, Desmos. So, for example, if you wanted to do y equals log base 2 of x, that would be the same thing as y equals ln x over ln 2. So this is the connection between all different kinds of logarithms. But one last example of this, and then we'll go ahead and call it a section. So an example, use a change of base to the natural logarithm to evaluate the following. To 5 decimal places. So for example, let's say we wanted the log base 1/2 of 0.1332. Well, if we want it to be the natural logarithm, that's going to be ln, and it's going to be ln 0.1332 divided by the ln of 1/2. And we can just use now a calculator to evaluate this. And the calculator you can use, it can be pretty much any kind of calculator, such as, for example, this one. And so here you can just zoom in a little bit, turn that off, get a better view. Okay, so then you just turn it on, and if you want something like this, you just type in ln and then 0.1332 divided by, and you don't have to do it in 2 steps, you can do it all in one, divided by ln 1/2, and you just press enter, and voila, you get an answer 2.90833. And if I want this to 5 decimal places, then that's going to be 2.90833. 5 decimal places. Alright, and that's going to do it for this episode of Math 111. Until next time, bye.